Okay, let's talk about the radar cross-section. Radar cross-section is an important parameter which defines the radar visibility of the object. It actually models the capability of scattering signals towards the radar of an object of interest. To define this, we are going to proceed in a similar way that we do in antennas. In antennas, we define the gain with respect to a simple conceptual antenna, which is an isotropic radiator. Here, in the case of radar, we are going to do something very similar. We are going to take as a reference target to define this radar cross-section parameter an ideal isotropic lossless object. We will represent this frequency with a sphere, because a sphere is almost an isotropic target, and if the sphere is metallic, it can consider almost lossless. So a sphere is the reference, if you want, to define the radar cross-section. Then, in the case this object is isotropic, once the radar illuminates the object, we can calculate the power density of incidence or illumination. Actually, we have here, at this point, if we transmit this power, PT, with a gain of the antenna, GT, range is this R parameter, which separates the radar antenna and the object. Then the incident power density is easy to calculate. It is actually the product of the transmitted power, the gain of the antenna, divided by 4 pi R squared. Then, what is the intercepted power that is actually obtained or captured by this isotropic object? Well, it will be simply the product of the power density multiplied by the geometric cross-section. So if you want the projected area of the target, which is a disk in this case. Okay, then we have intercepted this power. What's going to happen next? Well, it is a lossless target, so this power which has been intercepted has to be fully re-radiated, scattered. Because it's isotropic, the scattering takes place in all directions with the same gain, which means it's like an isotropic antenna which is fed with the power which has been intercepted. Then the total scattered power is equal to the intercepted power. The echo power density available on the radar will be the scattered power divided by 4 pi R squared. There's no gain because we have defined this object to be isotropic. Then we can put all the equations together and we get the final result. So the received power by the radar antenna is just the product of the incident power density on the antenna multiplying the area, the effective area of this antenna. We can cast this effective area in terms of gain, and then we get the following expression, which is in here, when we have the received power is proportional to the transmitted one. All the problem is linear at the end, so if we double transmitted power, we double received power. The gain of the antenna, of the radar antenna, appears twice because it acts as a transmitter and receiver. So if we increase 1 dB in this antenna, we get 2 dB of benefit at the end when we receive the echo. Then we have the area, projected area of our object, which is the cross-section, geometric cross-section of our isotropic reference target. And then we have this lambda square, which provides from this conversion between effective area and gain for the receiving antenna. And we have actually in the denominator, we have 4 pi to the third power and R to the fourth power. So this is a very important term in radar. This means if we increase range, the drop of the echo signal will be very, very significant, very important. So we have to take this into account in the radar design. Now, this was for a simple reference target. What's going to happen with a real target, like an aircraft, a ship, I don't know, whatever, a tree, for example? Well, things are going to be more complicated because this target is not isotropic. You see now the radiation pattern has a lot of maximum and minimum. And also, it does not to have, so it may have losses. So, and because of this, if we measure the geometric projection, for example, we have here the geometric section of this aircraft here, and we try to verify if the same equation is valid as in the previous reference case, it's not. So the received power is not actually reproducing the isotropic equation because this target has losses and it's not isotropic. Then, what is done actually to define the radar cross-section of this object, we use an equivalent model for this object in terms of the echo power. So what we find is, okay, what would be the size or the geometric area of the reference isotropic target that would equal the received power, echo power, in the real case, in the real target. So in this case, okay, we are not going to use the real geometric section, but we are going to use the same equation as before with a radar cross-section of this target, which is the geometric area of an isotropic reference target that is equal in terms of echo power to our real object, our real target. So, because this equation now it's the one we are going to use, sigma, this is the Greek letter that we use to denote the radar cross-section, will not be equal to the geometric area of the object in general. So we define radar cross-section as the geometric section of a reference isotropic lossless target, which delivers the same echo power as in the case, in the real case, we make an experiment with a radar. Notice that we have introduced an L parameter here in the denominator, and this is to model the additional losses which are not part of the target, which may be belong to the atmospheric channel or to the radar system itself. It is interesting to interpret the radar cross-section parameter as a product of three factors: the geometric cross-section, the efficiency, and the directivity. Why these three factors? Well, first, the geometric cross-section of the real target gives us the amount of power that has been gathered or has been obtained by the target itself. So this is the amount of power we have available. It has been captured from the illumination front. Then, what's going to happen with this power? Well, if we have losses, part of this power is going to be dissipated in heat, and part of this power will be re-radiated. But when this power is re-radiated, it is important to consider what is the directivity of this scattering or this re-radiation process, and this is the role of this third letter, this third parameter, directivity. We have here typical values of radar cross-section, depending on the size and the shape of the target, the materials of the target. We will have very high values. For example, an oil tanker ship can be up to 1 million square meters, and if we go to a very small object like an insect, we can have a very, very small radar cross-section. So the dynamic range of this parameter varies a lot depending on the size, materials, and shape of these targets. Radar cross-section can be obtained also from the ratio between the incident and scattered fields, using this expression here. This is used to measure actually radar cross-section of objects, and this parameter, sigma, will depend on the size, which will affect this geometric area parameter. It will affect also directivity. Will depend on the shape, which will affect also directivity mostly. The materials will affect the efficiency. Metals are almost 100% efficient. Natural substances like wood, human skin have efficiencies which are between 0 and 1, so 30%, 50%, things like that. Water can be more efficient, can be 70, 80%, depending on the frequency and the angle of incidence. And also depends on the frequency and the wave polarization. Here in the slide, you have a typical radar cross-section of some metallic objects. All of them have been considered with a size which is much larger than lambda. For the sphere, a metallic sphere, this is almost an isotropic. It's not perfectly isotropic, but it's almost like an isotropic object. So sigma it's actually equals the geometric projected area in this case, because the efficiency and directivity is 1, or almost 1. In the cylinder, you have also another expression. And we have also expressions here modeling the flat plate. The flat plate is an interesting object which can be extremely bright or extremely dark in terms of radar scattering or radar cross-section. If the flat plate is just orthogonal to the incidence direction, then we have, if we do an array analysis, the rays go straight directed towards the radar receiver antenna, and then we have extremely bright targets, so sigma can be extremely high. You see this expression here involves the area square divided by lambda square. So if it is electrically large, the area is much larger than the lambda square, then this parameter goes up to very high values. But if the same plate is obliquous with respect to the direction of incidence, then the rays goes directed to other directions different from the radar position. And then we get much lower values. Actually, this can be computed with this expression, which is a physical optics approximation. And depending on the angle, the final result of sigma can be extremely low. So the flat plate can be used to obtain a high or a very low radar cross-section, depending on the pointing. Now, at this point, it is also important to consider the frequency role. Notice that in the previous examples, we have mentioned that the object have to be electrically large to actually these expressions to be valid. Now, what happens if the objects are not electrically large? Okay, let's consider a simple object. In this case, what we have is a plot of the radar cross-section of an sphere, depending on the frequency of operation of the radar. Actually, the plot is a logarithmic one. You see here the horizontal axis. It is the perimeter of the sphere divided by the wavelength. The sphere has a radius a, so this is the perimeter normalized to the wavelength. It goes from 10 to the minus 1 in the left, more or less 1 in the middle, and 10 to the power 2, so 100 at the right part of the figure. And what we have here in the vertical axis is the sigma, the radar cross-section, normalized to the geometric area. And you see here, we can obtain, okay, we have 1 here at this point, and here 10 to the minus 3, so you get an idea of the difference of the values. So we have a large dynamic range plotted here. And okay, let's take a look to the shape of this curve. You see, you can actually define here 3 different behaviors, or 3 different regions. At the left, what we have here is a very fast drop of radar cross-section with respect to the geometric section of the sphere. This happens at the Rayleigh region, the so-called Rayleigh region, where the sphere is electrically small, so the perimeter is a fraction of the wavelength. And what happens in this region is, if we actually decrease frequency, we lose radar cross-section very fast. In the middle, we have the so-called Mie or resonant region, where the radar cross-section parameters fluctuates quite a lot around the 1 value here, which actually means 1 means a radar cross-section equals to geometric section of the sphere. And when we have this kind of a maximum and minimum behavior, more or less sinusoidal behavior, in electromagnetics we always suspect there is an interference between 2 different mechanisms. And this is actually what happens in the sphere. We have a frontal mechanism and a traveling wave, a creeping wave, which propagates around the sphere and is vectorially or fasorially added to the frontal mechanism. This means, depending on the phases of these 2 mechanisms are not the same, they are going to reinforce or tend to cancel each other. Actually, the creeping wave is not as strong as the frontal wave, so this means that the cancellation is never total. And when we increase frequency, this traveling wave role is decreasing with respect to the frontal mechanisms. It's going to be stronger or dominant. This means that actually this drops up to a limit when we don't notice any variation. And this happens at the optical scattering when the sphere is electrically large. So when the sphere is electrically large, it is true that the radar cross-section is equal to the geometric cross-section, but at other frequencies, that's not true. It is important to note that this behavior that has been studied here with a simple object like a sphere, you can actually observe it for other shapes of objects or complicated objects. For example, for an aircraft, of course, the details of the shape will not be like this, but you could identify still a Rayleigh, a resonant, and an optical region for other objects. So this can be extrapolated for other targets as well. And a curious example of this is, because this is electromagnetics, it can be applied in principle to any wavelength, also optical wavelengths. So if you look at the atmosphere, scattering of the light, of the visible light, which is provided by the sun, when we see the sky blue, why is the sky blue? Why is this color? Well, blue is the highest frequencies of the visible optical spectrum. And it is blue because the air molecules, so nitrogen, oxygen, CO2, etc., they are small in terms of the visible wavelength, which is half a micron, more or less. And because they are small, we are in the Rayleigh region. So in the Rayleigh region, we scatter better the highest frequencies, which are the blues, and we scatter lower the greens and much lower the reds, okay? So that's why the sky is blue. If we look to the clouds, the cloud particles are much larger than lambda. And in this case, we are in the optical region, which means the scattering is flat. So we scatter the same, all the colors, so that's why we see the clouds white. Okay, let's go to typical radar targets like aircraft. How are we going to obtain radar cross-section? Well, we have basically two options. We can measure or we can simulate, and we can model and simulate with a computer. Measurements can be done in several ways. We need an instrumentation radar. We have here one in our anechoic chamber department. When we have a calibrated radar with a compact range, which provides a plane wave on the radar. This is a model, a scaled-down model of a target on top of a low reflectivity pylon. It's basically a foam which is very transparent. So in this case, we rotate the target and we obtain this polar plot of the radar cross-section, for example. If we process this radar cross-section with imaging techniques, we will going to present them at the end, we can obtain high-resolution images. This is an F-18 fighter high-resolution image. And here in the scale here, you have the radar cross-section, and this is interesting because it identifies what part of the target actually contributes mostly to the radar cross-section. In this case, is the fuselage of the target, which has reasonably flat plates, metallic plates. An alternative will be to actually introduce a 3D model of the target to a computer and actually run algorithms in order to provide radar cross-section estimation or calculation. This is one of the works that have been done in our lab with the Greco processing environment, and that's the result of the Greco processing corresponding to a fishing vessel and X-band vertical polarization. Also, on radar cross-section, there are special situations, like, for example, this one. The radar, normally, most of the radars are monostatic. This means radar transmitting and receiving antennas are the same or are placed almost at the same position. But that's not necessarily the case in all radars. So some special radars are bistatic, which means the transmitting and receiving antenna are separated at different positions. In this case, we have to redefine our problem with a bistatic radar cross-section. It is the same, essentially, problem, but now we have two directions. We have the incident direction and the scattering direction. And we have two antennas. They don't have to be necessarily the same. So in this case, we just redefine, or we extend the concept of radar cross-section to the bistatic. So we talk about the bistatic radar cross-section. And then the equation we have to use is the one we have in here, which considers the bistatic radar cross-section, but also the gain of the two antennas, receiving and transmitting antennas, and also the ranges, which are not necessarily the same from the antennas to our target. But it is essentially the same problem. Particular cases of the bistatic situation is the forward scattering, when we have the receiving antenna just behind our target in the direction of incidence, and the backscattering, which corresponds to the monostatic situation when we have the two antennas are placed at the same position. Another particular case or extension of radar cross-section concept is the polarimetric radar cross-section. Remember, in electromagnetics, everything depends on the illumination, vector field, and also the scattering has not to be in the same polarization as the incidence polarization. So, for example, if we use linear polarizations, we can define here two possible incident polarizations, vertical and horizontal. Then the scattering will have vertical and horizontal components. It will be, in general, an elliptical polarization. And then if we measure the two components for the two possible incident polarizations, we extend the concept of radar cross-section to a polarimetric radar cross-sections, when we have the two diagonal elements corresponds to the same polarization, for example, HH and VV in the case of linear polarizations, and the other elements corresponds to the cross, for example, HV and VH polarization. The linear basis is a possible one. Another one is the circular polarization, where L stands for the left and right, R stands for the right polarization. Some radars use linear polarization, some other radars use circular polarizations as well. This is an example of a polarimetric radar cross-section measurement that corresponds to the Boeing 747 scaled down model, which has been measured from 12 to up to 40 gigahertz in an anechoic chamber. You see the most important parameters or highest values are obtained at copolar, HH or BB. In the cross-polar components we have a less contribution, and most of the contribution is at the fuselage orthogonal incidence area, where this aircraft actually is providing the highest values of the radar cross-section. You have here at the bottom the calibration in color. To finish this radar cross-section presentation, we have to take into account that real targets are very complex. In general, we are not going to know the precise orientation of the target with respect to the radar. So from the radar design point of view, it is very interesting to characterize statistically radar cross-section. And this is done in pulsed radars in several ways. Swirling models are the classical approach. It was introduced in 1954, and actually the models are based on the probability density function and the autocorrelation, the time autocorrelation of the radar cross-section of targets. So there are four models that were proposed. Swirling 1 and 2 are built on a model of a cloud of random scatters. So they provide a Gaussian, real and imaginary part of the field, of the scattered field. Then the amplitude is a Rayleigh, has a Rayleigh probability density function. And the power, because actually radar cross-section actually affects directly power, received power, becomes an exponential PDF. Then in the case of the Swirling 3 and 4, the model is slightly different. We have still a random cloud of scatters, but we add now a dominant scatter here in the center of the cloud. And then the resulting PDF, it's different. It's a chi-square degree 4 power PDF, which is this expression here. Now, this actually is for, the difference between 1 and 2 and 3 and 4 is the model and the resulting PDF. Then you could think, okay, but what is the difference between the 1 and 2 and the 3 and 4 models, swirling models? Well, in this case, the difference is related to the correlation. So how fast, the autocorrelation, how fast the radar cross-section changes with time. So swirling 1 and 3 are slow varying targets. So radar cross-section change slowly, so they can be considered completely correlated in a pulse-to-pulse basis, which means in time span in the order of milliseconds, but they correlated from one scan to a next scan of the antenna. The period of the scan of the antenna is typically a few seconds, 5-6 seconds typically. So this corresponds to a slow target. Other targets has a very fastly changing radar cross-section, And Swirling 2 and 4 models these targets considering that the pulse, or from a pulse to pulse, radar cross-section is absolutely decorrelated. So we have a completely new result. This could correspond to a very agile targets. For example, small aircraft or helicopters could be considered Swirling 2 or 4 because they change very fast. Other usual radar cross-section distributions can be variable, Hankel distributions, log normal, etc. They have been proposed and studied by different researchers corresponding to different targets or clutter.